Hello, and welcome back to the course on quantum mechanics. We are still in the fifth chapter for this course. So before we proceed with today's lesson, let us first review some concepts. So in the previous lesson, we have presented the or introduced the idea of spin statistics for different scenarios. So if you have distinguishable particles, you use Maxwell-Boltzmann statistics, which is a classical statistics. And if you have identical particles, then you use Bose-Einstein for bosons and Fermi-Dirac statistics for fermions. So in this lesson, we will be talking specifically about quantum statistical mechanics. So in this lesson, we will just be focusing on a small number of particles, and we will just generalize that concept later. So a general problem in statistical mechanics is this one. So if there are n particles in thermal equilibrium at temperature T, what is the energy of the particle chosen at random? So you have n particles, then you choose one particle out of those n number of particles at random, and what's the energy of the particle chosen at random? So of course you are not you're not gonna expect a definitive or deterministic answer. So the answer to this is a probabilistic answer. You can't answer it with a very specific say energy. So you can just say the energy could be like this because this has the highest probability. So the fundamental assumption of statistical mechanics is that in thermal equilibrium at a certain temperature T, every distinct state or wave function with the same energy E is equally probable. So what this means that in statistical mechanics, temperature is basically energy, because that's if you recall in your statistical mechanics, one of the fundamental equations there is E is kT, the thermal energy. Energy is kT. It's basically temperature. Okay, so this means also that it does not favor statistical mechanics, does not favor any particular state. So you only have random thermal motions. But again, if they have the same energy, then they are equally probable. So in quantum statistical mechanics, it's basically counting states, counting distinct states. And the number actually depends on whether the particles are distinguishable or identical. So we will introduce the concept of occupation number, n sub n. So it's basically the total number of particles in a single particle state psi n. How many particles are in the single particle state psi n? And the collection of all of these occupation numbers is what we call the configuration. So the set of all occupation numbers of a system is what we call the configuration. Okay, going back to this question. So the answer will be the probability of getting a single particle energy En. So that is the answer to that question. What's the energy of the particle chosen at random? So of course you answer with probability. So in order to get the probability of getting a single particle energy En, we need to sum over all possible configurations and multiply the probability of the system being in that configuration times the probability of getting the single particle energy En in that configuration. So we usually, or I summarize that into PCI, the probability of the system being in that configuration, and PENI, the probability of getting En in that configuration. So the probability of getting of the system being in that configuration is just the number of system states in that particular configuration over the number of total number of system states. And the probability of getting En in that configuration is just the occupation number of particles for a specific single particle energy En or state psi n over the total number of particles. So that one. So we need to emphasize here that psi n is the single particle state, En is the single particle energy. And actually, if you have a system state, it will actually have many subscript depending on how many particles you have. So it's a function of R1, R2, R3, and so on. And if you have a system energy, the energy of the system is actually the sum of the individual single particle energies. Okay, so let's go directly to an example. So you have three non-interacting distinguishable particles with the same mass, and they are bound or trapped in a one-dimensional infinite squarable potential. So if the total energy of the system is 363 pi squared h bar squared over 2 ma squared, list all the states and all the possible configurations. What is the most probable configuration? What are the allowed single particle energies? And if you select one particle at random and measure its energy, what is the most likely value that you will get? Okay. So for a single particle state, you have psi n. So the psi n for a single particle trapped in an infinite squarable potential is given by this one. A single particle energy is given by this one, n squared pi squared h bar squared over 2 ma squared, where n starts from 1 to infinity. Okay, so therefore for the system state, since there are three particles, then you have psi, Na, Nb, and C. And then for the system energy, you have the summation of the energy of the three particles. So we will name the particles as particle A, B, and C. So particle A has an energy of Na squared, pi squared, h bar squared over 2 ma squared, and then particle B and particle C. We will get that. Now, the restriction for this problem is that the total energy is equal to this one. So this total energy, the system energy, must be equal to this one. Therefore, Na squared plus Nb squared plus Nc squared is equal to 363. So, what are the possible values of Na, Nb, and Nc such that if you add their squares, it's equal to 363? And you will actually have 13 possible combinations. So meaning, if there are 13 combinations for Na, Nb, and Nc, then there will also be 13 system states. Okay, first question, list all the states and all the possible configurations. So these are the list. Okay, so the states can actually be categorized into 4 configurations. The first configuration is, again, this is just a set of all occupation numbers. When all of the 3 particles are in state psi 11. That corresponds to this state, psi 11, 11, 11. Again, since this is the distinguishable case, just multiply the 3 single particle states. So psi 11 times psi 11 times psi 11. So that is the first configuration. The second configuration is if one of the particles is in state psi 5 and 2 of the particles are in state psi 13. So the occupation number for the state psi 13 is 2. The occupation number for the state psi 5 is 1. So there are 3 possible combinations for that scenario where one particle is in state psi 5 and 2 particles are in state psi 13. So you will have psi 5 13 13 and psi 13 5 13 and psi 13 13 5. A similar scenario happens when 2 of the particles are in state psi 1 and 1 particle is in state psi 19. And in that scenario, it has also 3 possible combinations. So you have 1 1 19. So it's either particle A is in psi 1, particle B is in psi 1 also, and particle C is in state psi 19. Or particle A is in psi 1, particle B is in state psi 19, and particle C in state psi 1. Or A is in 19, B is in 1, and C is in 1. The last configuration is when one particle is in state psi 5, another particle is in state psi 7, and the other particle is in state psi 17. So this configuration has 6 possible combinations, or 6 states, 6 system states. So you have 5, 7, 17, 5, 17, 7, and so on. So all in all, if you add the number of states, you will actually have 13 states corresponding to 4 configurations. So we can now then try to find the probability of the system being in that configuration. So it's just the number of states in that configuration over the total number of states. So in this configuration, for example, there's only one state out of 13, so 1 out of 13. So for this state, you have 3 states out of 13, 3 states out of 13, and this is actually the most probable configuration because it has 6 possible states. So this state will now be the answer to letter B. What is the most probable configuration? So this is the most probable configuration. So you answer this one. Okay. And for the letter C question, what are the allowed single particle energies? Then you will notice that there are only certain single particle energies that are allowed. So 1 is allowed, 5 is allowed, 7 is allowed, 11 is allowed, 13 is allowed, and 19 is allowed. So there are actually 7 allowed single particle energies: E1, E5, E7, E11, E13, E17, and E19. The rest of the single particle energies are not allowed. So E2 is not allowed, E3 is not allowed, E4 is not allowed. Okay, for the letter D question, if you select one particle at random and measure its energy, what's the most likely value that you will get? So basically, you are trying to find the most probable single particle energy. So to find the most probable single particle energy, we need to solve for the probability for each of the allowed single particle energies using this formula. So PCI is the probability of the system state being in that configuration. PENI is the probability of getting EN in that configuration. So let's start with E1. So for E1, you will notice that there's only one configuration. So take note, this is summation over all. I here is the configuration. You sum over all the configurations. So since E1 is only present in one configuration, this the third configuration, then the probability of this configuration is 3 out of 13. So 3 out of 13 multiplied by probability of getting EN in that configuration. So it's basically just occupation number over the total number of particles. So the occupation number for 1 is 2 divided by the total number of particles 3. So 2/3. So you will get 2 out of 13. Now, the next allowed energy is E5. Now, for E5, you will notice that it's present in 2 configurations, in the second configuration and in the last configuration. So we'll have to sum over these 2 configurations. The first in the summation is for the second configuration. So in this configuration, the probability of this configuration is 3 out of 13. And the probability of getting EN in that configuration is, so there's only 1, 5. The occupation number for psi 5 is 1. So 1 out of 3. And then plus the next configuration. The probability of this configuration is 6 out of 13. You multiply it for the probability of getting EN in that configuration. So E5, the occupation number of psi 5 is 1 out of 3 particles, so 1/3. So you will get a total of 3 over 13. So you do the same for the other allowed energies, and you will get these values. So you will notice here that if you add all of the probabilities, you should get 13 over 13 or 1. And you will notice also that the highest probability is 3 out of 13, which corresponds to the probability of getting E5. So meaning, the most probable single particle energy is actually E5. So if you select one particle at random and measure its energy, the most likely value that you will get is that particle has this energy, 25 pi squared h bar squared over 2 ma squared. Of course, the probability of that is only 3 out of 13%. But that is already the highest probability among the allowed single particle energies. Okay. For example, number 2, the same problem, but it's now identical bosons. So you list all the states and the possible configurations. So in this case, since if you have identical particles, there's no longer a degeneracy, meaning one configuration now corresponds to one state. So all of the possible combinations are now of 5, 13, and 3 are now taken into account in this state, psi plus 5, 13, 13. So one configuration, one state. So there are only 4 states in this case if you have identical bosons. And each of the configuration corresponds to one state, meaning the probability of each of the configuration is 1/4 or 25%. So all configurations are equally probable since they have the same probability. And this actually features the quantum mechanics, wherein in quantum statistical mechanics, or if you use quantum statistics, one configuration equals one state. So the allowed energies are actually the same with the distinguishable case. And if you, in this case, if you try to find the probability of each of the allowed energies, E11 will have the most or the highest probability. So if you now go to if the case is now identical fermions, 3 identical fermions. So take note that identical fermions cannot occupy the same state. So 11, 11, 11 is not possible. 1, 1, 1, 19 is also not possible. 13, 5, 13, 13 is also not possible. So there's only one possible combination if the 3 particles in this problem are identical fermions. So the state 5, 7, 17. And again, since this is now quantum statistics, we already took into account all of the possible combinations of 5, 7, and 17 in this state psi minus 5, 7, and 17. So there's only one configuration, there's only one state, so meaning this is the most probable configuration. And the allowed energies are only 3. So E5, E7, and E17. And all of these 3 are all equally probable. So they actually have the same probability, 1/3, 1/3, 1/3, 1/3. So they are all equally probable. Okay. So from example 3, so from the previous example, construct the completely anti-symmetric wave function psi minus 5, 7, 17 for the 3 identical fermions. Okay. So let's now go to finding the wave function of a 3-particle system in general before we answer this question. So plus operation corresponds to boson, minus operation corresponds to fermions. So basically just take into account all the possible combinations. So you have A, BC, CB, and then B, CA, BAC, and then C, AB, C, BA. So that's all the possible combinations. So plus is for bosons, minus is for fermions. So if you take into account that one, so if the 3 states psi NA, psi NB, and psi NC are all distinct states, distinct from each other, then A here is 1/square root of 6. So in the case of fermions, the 3 states psi NA, psi NB, and psi NC are always distinct. They cannot be the same. But in the case for bosons, and psi NA, psi NB, and psi NC can be the same. So For bosons, if psi n b is equal to psi n c, such as the state 1119 and 51313, where two of the states are equal, then from this equation, from the starting equation, if nb is equal to nc, then you will get this one. So if two of the states are equal, then you will have this wave function for the three-particle system. Now, also, if the three states are equal, such as in the example number 2, wherein you have psi 11, 11, 11, then from this starting equation, for our first equation, if psi n a is equal to psi n b is equal to psi n c, then you will get the final wave function for bosons as just basically the same as the distinguishable case, psi n a, psi n a, psi n a. So the three states are the same. For fermions, it's just this one. So no two states, no two particles can occupy the same state for a fermion. So it's always this formula. So you have 1 over square root of 6, and then there's a subtraction operation here. So even though these states, the single particle states, psi 5, psi 7, psi 17, are for a single particle trapped in a one-dimensional infinite square well potential, but you don't need to expand this one because it will be very long if you expand that one. So this answer is already enough. Okay. So by the way, as a note, this wave function is anti-symmetric. So if you interchange two particles, this will result in negative psi, negative wave function. So for example, if you interchange 7 and 17, you will get negative psi. So a continuation for example 4. So from example 2, the case of identical bosons, construct the completely symmetric wave functions of the three identical bosons. So this is our formula if the three states are distinct from each other. This is our formula if two of the states are distinct, and this is our formula if the three states are all the same. We have three formulas for bosons. So for the state psi plus 11, 11, 11, you just have psi 11 times psi 11. For the state psi plus 5, 13, 13, then you use the second formula. The same also with psi, the state psi plus 1, 1, 19, you use the second formula. And for the state psi plus 5, 7, 17, you use the first formula, the longest one. That one. So these states are actually symmetric. These wave functions are actually symmetric. So if you interchange any two of the particles, you just obtain the same wave function. So that's what symmetric, so that's what identical bosons means. They have symmetric wave functions. Identical fermions have anti-symmetric wave functions. Okay, and that is the end of the lesson. So for the next lesson, it will be about generalizing what we discussed in this lesson. So we will now generalize quantum statistical mechanics if you now have an infinite number or a large number of particles. So I will see you again in the next lesson.